Have you ever noticed how a hot cup of coffee left in a cool room always cools down over time? It never heats itself up. This simple observation is explained by the second law of thermodynamics. The key concept here is entropy, a measure of disorder in a system. The second law tells us that entropy always increases in natural processes, meaning energy spreads out and becomes less useful over time. This is why the second law is so important in engineering. It helps us design more efficient systems like engines and refrigerators by minimizing energy losses. Second law of thermodynamics isn't just about energy, it's about limit and possibilities. It explains why energy degrades and why perfection is impossible. But more importantly, it shows us how to improve and build smarter systems. That's the key to shaping a more efficient world. So let us now move on to example question. Describe an imaginary process that violates both the first and the second laws of thermodynamics. Imagine a perpetual motion machine that powers itself and does external work without any energy input, while simultaneously cooling itself and becoming more ordered over time. Such process is impossible because energy cannot be created or destroyed, and entropy in an isolated system can never decrease.
So now I'm going to talk about thermal energy reservoirs. What is actually a thermal energy reservoirs? They are bodies that can absorb or release heat without experiencing significant temperature changes. Examples include large bodies of water like oceans, lakes, and rivers, as well as the atmosphere, which can take in or give off heat without noticeable temperature shifts. For instance, in winter, residential heat losses don't significantly warm the atmosphere, and power plants dumping energy into rivers barely change the water's temperature. Now, let's move on to types and applications. Thermal reservoirs can act as either sources or a sink. A source provides heat energy while a sink absorbs it. For example, industrial furnaces are excellent sources because they supply large amounts of heat at nearly constant temperatures. On the other hand, rivers and lakes often act as sinks, absorbing waste heat from industrial plants or power stations without large temperature changes. These reservoirs are crucial in designing efficient energy systems such as power plant and heating system. Let's look at the example question. Consider the process of baking potatoes in a conventional oven. Can the hot air in the oven be treated as a thermal energy reservoirs? The answer is no. The hot air in an oven cannot be treated as a thermal energy reservoirs because it has a limited capacity to hold heat. Its temperature changes significantly as heat is transferred into the potatoes, and it relies on the oven's heating system to maintain a steady temperature.
Next, we will learn about the Carnot cycle. The Carnot cycle is the best known reversible cycle, which is an ideal heat engine cycle, and it is proposed by Sadi Carnot in 1824, a French engineer. And in theoretical heat engine in Carnot cycle is called Carnot heat engine, and it is composed of 4 reversible processes, and it uses ideal gas as a working medium. It also called as a perfect engine as it has no friction in between cylinder walls and no heat transfer. The first process is called reversible isothermal expansion. The condition is the temperature of the gas and the energy source is the same. So, the gas inside is allowed to expand. When gas expands, it works on the surrounding. So, pistons move to the right. As the gas is expanding, the temperature begins to decrease, but heat is transferred from our energy source back into the gas. So, pH is constant because the temperature difference between the energy source and the gas never changes more than in infinitesimal amount. So, it is a reversible heat transfer process. And the total amount of heat transferred is called QH. The second process is called reversible adiabatic expansion. So, we remove the energy source, we replace it with insulation, so it becomes adiabatic. Adiabatic means without heat transfer to or from the system. The gas is still expands and drops in temperature, TL. So, there is no friction between the piston and the cylinder, and that's why the process is reversible. The third process is called reversible isothermal compression. So, the insulation is removed and the cylinder is now in contact with an energy sink at temperature TL. The energy sink temperature is the same temperature in gas. The external force pushes on the piston, so it moves to the left. As the gas compresses, the temperature begins to rise, but as it rising, heat is transferred to the energy sink. Temperature remains constant at TL because the temperature difference between our energy sink and the gas never changes more than infinitesimal amount, so it is a reversible heat process. The total amount of heat rejected from the gas, we call it as QL. The fourth process, we call it as reversible adiabatic compression. So, the low energy sink is removed and the insulation is placed back on the cylinder head. So, the gas continues to be compressed and goes back to its initial state. The temperature rises from TL to TH. So, the cycle is now complete. So, we will learn about Carnot pressure volume graph. The first step is 1 to 2 from the first process. The pressure drops and the volume increases as the gas expands. The temperature stays constant at TH and heat needs to transfer from energy source QH. The 2 to 3 step is from the second process and the pressure drops more. The volume continues to increase. The cylinder is now insulated, so the temperature drops to TL. The 3 to 4 step is from the third process. So, what is it going? The piston is pushed inwards and the gas is compressed. As the pressure increases, volume decreases. There is an energy sink, so the temperature is kept constant at TL. The heat is rejected from the energy sink. Now, the steps 4 to 1 is from the fourth process. The cylinder is insulated while the piston is pushing inwards. The pressure continues to increase. The volume continues to decrease to arrive at state in 1. Now, the temperature rises to TH. Now, the area inside the bath is the net work done during the cycle. Since it can be a reversible cycle, it can result to Carnot refrigeration cycle. The difference, the negative direction, is QL is heat absorbed from a low temperature reservoir and QH is heat rejected to a high temperature reservoir. Now, we will jump into the example question. The question is, what are the 4 processes that make up the Carnot cycle? The answer is, the 4 processes that makes up the Carnot cycle are reversible isothermal expansion, reversible adiabatic expansion, reversible isothermal compression, and reversible adiabatic compression.
The Kelvin-Planck and closure statements of the second law of thermodynamics lead to 2 important conclusions about the thermal efficiency of heat engines. These conclusions are formalized as the Carnot principles. The first principle states that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same 2 reservoirs. The second Carnot principle states that the efficiencies of all reversible heat engines operating between the same 2 reservoirs are the same. These Carnot principles can be proven by showing that violating either principle will result in a violation of the second law of thermodynamics. Proof of the first principle. Assume an irreversible heat engine is more efficient than a reversible one operating between the same reservoirs. This implies a reversible heat engine delivers more work than a reversible one for the same heat input. The reversible engine then was reversed to act as a refrigerator, consuming reversible work to reject heat input to the high temperature reservoir. Since the irreversible engine absorbs heat input and the refrigerator rejects heat input, the net heat exchange with the high temperature reservoir becomes 0. This allows the elimination of the high temperature reservoir by having the refrigerator discharge heat input directly into the irreversible heat engine. The combined system would produce net work irreversible work minus reversible work while exchanging heat with only the low temperature reservoir. This violates the Kelvin-Planck statement of the second law. Therefore, the assumption where a reversible heat engine is more efficient than a reversible one operating between the same reservoirs is incorrect. Proof of the second principle. The second Carnot principle can also be proved in a similar way. Replace the irreversible engine with the reversible engine that is more efficient. Following through the same reasoning, combining the more efficient engine with the reversed, less efficient one would end up having an engine that produces a net amount of work while exchanging heat with a single reservoir, which is a violation of the second law. Let's answer a question. This claim can be evaluated by referring to the second Carnot principle. First, assume that the new reversible heat engine is more efficient than the Carnot cycle operating between the same temperature limits. Next, reverse the new engine and let it function as a refrigerator. This refrigerator will require a work input to reject heat to the high temperature reservoir. The reversible heat engine absorbs heat input and the refrigerator rejects the same amount of heat input, resulting in 0 net heat exchange with the high temperature reservoir. At this point, the high temperature reservoir can effectively be eliminated and the refrigerator can discharge its heat directly into the new reversible engine. The combined system of the refrigerator and the engine would now produce a net work output of work new minus work Carnot while exchanging heat with only the low temperature reservoir. This situation clearly violates the Kelvin-Planck statement of the second law of thermodynamics. Therefore, our initial assumption is incorrect. We can conclude that no heat engine can be more efficient than a reversible heat engine operating between the same temperature limits. Hence, the claim is invalid.